welcome the people for a while. So they are, I guess, used to my same old opening slides, but I feel like I need to share them.
We have already 22.
Yeah, right at 9 o'clock. So good morning, everyone. It's very nice to have you all here. And today is the last day of our learning week. It's a bit sad, actually. And we have a great session this morning. So we have Achim Kraus today, and he will walk us through around the power consumption of different IoT protocols. So briefly about Achim, but of course he will also explain himself. He is a CoAP and DTLA cloud expert with more than 25 years of experience in software development and more than 7 years of experience in IoT area, and a lot of knowledge that I already spent a lot of time this morning to ask my questions towards him. So I'm very glad to have him for this session and very glad to introduce him to you.
Thanks for the introduction. So also a warm welcome to everyone from my side. My name is Achim Kraus. I'm a software developer. I do professional software development now for about 25 years. I had started with something similar like IoT. I would call this an embedded distribution system. I think it's 20 years ago. So I have already also a lot of experience in doing communication between embedded devices, even if it was not the internet. And in the last 8 years, I was working on one of the most interesting protocols. It is this CoAP stuff, DTLS. I was working on open source implementations of that, especially on the Eclipse platform. It's the project Californium, which offers you a Java implementation of CoAP and DTLS. And last year, I also joined the tiny DTLS of Eclipse. This is a C implementation of DTLS in order to make it better that you can really have a stack which have comparable and compatible features from end to end, which means from the device to the server. So let's start with my slides. So what's about? I want to give you a view how we can compare the power consumptions for several IoT protocols. As I said in my introduction, I'm focused really on CoAP, DTLS, and UDP. I'm no TLS or TCP expert, so it may be that especially those results for TCP that someone else can do this much better, but I hope it gets at first, it's just the first thing you have to get first numbers. So what's about power consumption? I decided to make first an example which is not an IT example. So what I like to introduce you is something like how we do a model of power consumption and how we can use this to reduce the power consumption. So for me, the use case is we have a car, and this car has an engine, and the engine runs on power if you drive the car. That has the highest power consumption then. Usually, if the car is standing, the engine runs idle, and then it has a low power consumption. And sometimes, if the car is parking, we switch off the engine for sure, and then we have no power consumption. So we see that we have different modes, and we see we have different consumptions. And the strategy now is just that we try to switch to a mode with lower consumption. Yeah, as frequently and as long as possible. So if you switch the engine from power to idle while you're driving, I think the point would be that driving will stop. So this is no possibility. But I think it's very common that people started to think that if the car is standing and the engine runs idle, that we can switch it off. That's the main case now for saving energy in this example. Okay, there is a downside because if you restart the engine, this is not for free. So the saving depends on something like how long is the engine off and how is the efficiency in the restart of this engine. I think when this was discussed, I guess it was 20 years ago, many denied that you can have any savings with this idea at all. And they say, okay, you damage the motor, but you don't save fuel. I think that the technical evolution at that point then starts, and they improved and improved and improved. And as of today, a modern car has usually a start-stop automatic, which improves this restart efficiency very well, and which also makes it very comfortable to be used. So according to a German paper, a German club, the Automobile Club of Germany, this is this ADAC, they say now you have, with this technique, you have in city traffic a saving of 15% energy. You may discuss this if this is true or not, but I think that's something we can trust on. So the point is, we have several levels. We try to get into the lower ones. Basically, we need to optimize the stuff. Basically, we need to get things more efficient. And I think that's the basic for power consumptions, also for IoT devices. So switch to the next slide. I think here we have the power consumption of a modem-based IoT device. A model is just a simplification, so maybe the one or other thinks this is not that easy, but this model should just make you focus on the things where the transitions happens and where you can save energy and where perhaps you need improvements. So this model has something like an active state. This is when you transceive and receive data and your CPU runs, then you have a really high power consumptions. There is also as usual something like an idle state. This basically means that the transceiver and receivers are not active and the CPU is only partial active. The power consumption with that is pretty low. And then we also have a state which is called sleeping. Then you also have no transceiver and receiver enabled and the CPU is sleeping. With that, you have really an ultra low power consumption. I think you should look up this in the data sheet of the modem or of your system. This is usually something like 2-4 microamperes. It's not that much. It's really cool. Or we can switch off and then we have close to really no power consumption. So also here, the idea is switching to lower modes as frequently as possible. And also here, the main case is that we basically switch from idle, if we do not do too much useful things, into sleeping or off. And also here, it's the point, if we switch to active again, this requires energy. And so again, the factors, if this works or not, is more about how long do we sleep or are we off and how efficiently we are when we reactivate the device. So the model for the modems is a little more complicated because we have here now several layers and all these layers are affected by switching off and on or by going to sleep. So we have the mobile network where we have to attach the modem. When I wrote these slides, I used the term reattach. This is wrong. This is, it doesn't use a reattach, but yeah, I don't think this makes it too much difference. We have an IP protocol, there we have TCP, UDP, and we have IP addresses. This makes also a difference. We have encryption, we have TLS, DTLS, and WSCORE. We have then protocols on top of that, CoAP, HTTP, MQTT-SN, and MQTT. And we have also an application backend, I will say something which stores data, fetches data, or process data. A lot of that stuff is not really my domain. I think WSCORE is something I don't do. MQTT-SN and MQTT is also nothing in my domain. I think there are other experts who can do this better. So my comparison is basically HTTPS, CoAP-S with DTLS and DTLS connection ID. So the power consumptions, so all what I say is something like based on real world examples. So it's not a too theoretical paper. So I just use, I think, a very common tool. It's a Nordic modem, the NRF 9160. I use the development kit of that because with the development kit, it's really very, very easy to make your own power measurements. This is really, from my viewpoint, cheap and easy to do. I use the modem firmware 3132, and I use, I think it's the current one, the Nordic connector software. It's the V version 210. There is also a very cool tool. This is this power profiler kit from Nordic. I like this because it's really affordable. It's about 100 euro or a little more, maybe 150. I don't know the current price, but it is really a nice tiny tool which helps you a lot to understand the power consumption, and which helps you a lot to do the stuff. And there's also application from Nordic. I currently use the Power Profiler version 352. Because it's not only about the overall power consumption from starting the communication to have the modem going down. It's also sometimes interesting which phases takes how much energy. Therefore, I added to my examples 2 signal lines. So one signal is signaling the application level, something like the application starts to send data, and something like the application has now the response received. And also another indication which reflects the RRC connection state to the mobile network. That's more or less something like when the modem is really active. My measurements, I don't consider them to be normative. This means these are just example measurements with my signal strength here in South Germany, only done with one modem. So even if I do this in retries, we get a bandwidth of values. This is also not clear what causes these differences. So from my side, I think if you have other modems or other mobile providers or whatever, it is just an idea how you can do your own measurements in order to ensure that you don't have 2 different results. The results I presented at the end of these slides in some tables, they are done by executing this test 4 times and taking the average. Yeah, as I said, I think this whole setup is more an idea how you can do it. If you have other variants to check, maybe there's also something common like only a one-way message to the cloud and don't wait for anything back. But this is not done here. If you want to do such things, I think this would be a frame where you can try to check what your variants will use as power. Okay. And also to say, all these measurements and the statistics, they help to build a forecast. What will be the power consumption if you run a device for longer? But it's also my experience, you need to run the device really for longer. So I did in summer a test about 4 weeks or 7 weeks, and then you see how good your numbers are really matching a long-term way. Okay. So I think the first layer we had, or the lowest layer, was the mobile network switching to active. And there we have the situation, we compare 2 variants. The one is switching the modem on and off. And this requires to attach the modem to the network. And we have to be aware that sometimes the network limits such number of attachments over time. So if you can really, the strategy to switch the modem on and off depends a lot on your network operator. Sometimes it's not that good, or it depends on how frequently you do this, but it is one of the strategies. The other one is using PSM. This means waking up the modem from sleep mode. I wrote here, this requires a reattachment of the modem to the network. This is wrong. The term reattachment is not the right one, and I didn't really found the right one, so just forget it. Here the downside is that some networks are reported that they don't support PSM, especially when you're in roaming. So my experience is not that bad and also not that wide. So I can say that in the most European countries, so yeah, have mostly tested this in Europe. In the most European countries, PSM is supported. But maybe there are also places where it is not supported. So yeah, take care. I think the point is you always need to where you run. Yeah, and also talking about a mobile network, sometimes there is also a network search required, but this is not considered here in this power consumption statistic. So I tried to measure without such network searches. So now just go into my very first measurements. This shows the time and the power consumption which is needed to get the modem connected to the RRC connected state. Here also the text full attachment is not, that's not the case, and also reattachment is not completely true with this. This basically means it's RRC connected, and if we use this on-off mode, and then my measurements on LTE-M showed that it takes about 1 second and it takes about 7.6 millicoulomb. If we do it with the power saving stuff, then it's shorter. It takes only 0.6 seconds and 7.3 millicoulombs. So we have a question: should we just check this or not? Okay. Okay, thanks. So we have now the explanation. It's not a reattach. It's just tracking error update or moving the connection mode. Thanks. So I think we see here that there is not a that large difference between the two. So go to the next slide. So IP switching to active. Here we have a situation which is not always the same. So if you use IP in a public network and you usually get a new IP address after a wake up. If you use it in a private network, this doesn't happen. But sometimes it's always not that possible to have it as private network. If the address is changing, then for TCP you require a new connection, for UDP not. If the address is changing, you usually require a handshake for TLS and DTLS, and maybe some say you can use an abbreviated handshake, but for me that depends a lot on if you really can use this on the stack you're using, means on your device implementation, on the service you want to use. If you use this new one, this stuff which I have developed, and also I have specified or worked in specifying the RFC with this is the DTLS 1.2 connection ID, then it doesn't require a handshake for requests after initial handshake. So yes, the reattachment is done after the PSM mode. I was trying to distinguish what happens after on-off and what happens after PSM. Oh, now I did something wrong.
Yeah, I guess you need to share the screen again. Yes.
Yes. I think sitting on the notebook with the touchpad is also not something I'm too common. So sometimes I don't.
I can imagine.
Okay. So that's the IP layer. Right. And that service. So, and the measurements here are also very easy. You see we have LTE-M, we use HTTPS, we have a full handshake, and in my measurements, this was something like, it takes 4.4 seconds in 137 millicoulombs. If instead you use this other version, this other variant to this other protocol. It's also LTE-M. We have CoAP DTLS connection ID. This connection ID is important at that point. Then it takes only 0.7 seconds and it only consumes 70 millicoulombs. So we see here is a large difference between the protocols. I think that's very useful or very clear, because a full HTTPS handshake exchanges about 20 messages, while you can do it with CoAP DTLS connection ID, you can come down to 2 messages. As I said, a lot of people say you don't need a full handshake or whatever, but to be frank, as long as they do not really make demonstration of what they say, it's really hard to follow this. So I was not really able to use an abbreviate handshake on this modem, but maybe someone with more knowledge in this domain can do this. So it's here something about the details. If we use TLS 1.2 in X509, so this means we have to transmit an X509 certificate to authenticate a server. And this happens always in a full handshake. And in my experience, this really reflects a common case. As I said, there may be other variants, but yeah, it's hard to get them really working. I execute a GET request. It's the simple one. It's the HTTPS example org. Basically, it's the same HTTP client as in the examples of that modem. So the request takes about 64 bytes. The response is about 370 bytes, and the server certificate has 3Ks. And there's also a little more overhead using TLS and TCP. Generally, also pre-shared key would work as authentication, but it's hard to find libraries and services. So it seems that this is not that easy to use this. PSKey would use much less data because you don't need certificates. It's also said that abbreviate handshakes tickets or resumptions may be used, and they also don't need them the certificates again. But it's really hard to find really demonstratable solutions, and therefore I didn't really go that way. So maybe or even TLS 1.3 may improve the situation, but it's also hard to get at. So should we go to the next question?
Recording in progress.
Yes, the point is I only worked on PSM and not on DRX, so I cannot give you any information what eDRX will help or not. Okay, so next point, this was this alternative protocol. Usually, if you use DTLS 1.2, the PSK variant, pre-shared key, RFC 4279, for authentication is used. The point here is this is really supported by the most DTLS libraries, so that's the difference. So for TLS, it's also defined, but to find really a supporting library for the server and the device is not that easy. For DTLS, it is easy. You will always, in my experience, you will always have this. So if you use PSK, you don't need an X509 certificate, and that helps you a lot to reduce the power and the data which is needed for the transmission. The tests are using a CoAP post request. I usually use the Eclipse Californium sandbox for such simple tests. You can also use this. This is a sandbox run by the Eclipse organization. You have here the address for that. The test sends about 430 bytes and gets 40 bytes back. So it's vice versa. The other one was sending less and get more, and this one sends more and gets less, but I don't think this should make a large difference. And also here, the DTLS layer and the UDP layer, they add some more bytes overhead, but for me, that's not that significant. And if we now use this advanced mode, this DTLS connection ID stuff, then the point is that we basically need a handshake initially, and after that, we use the connection ID instead of the IP address, and that obsoletes that we need always fresh handshakes. The implementation state is not that really nice. So in Eclipse Californium, that's my responsibility. It's now in for 3 years. I have prepared a feature branch for Eclipse Tiny DTLS. I think it's also now 1 year, and I use both, and for me, both runs very well. We have also a pull request pending for embed TLS. I think that will be the most interesting stuff for many people, but the pull request is still pending. It's I think it's up to the embed TLS team to process this, and I cannot really help them. What is also to say, if you use DTLS connection ID, you need to care about some upper layer stuff. So lightweight M2M or the CoAP observe notify stuff, because sometimes the upper layer also refers to the IP address in some functions. So say the notification is only accepted if it's from the same IP address. But though the IP address will change, then it may be not accepted. So if you want to use DTLS connection ID, you need to check each function if they use the address for identification of the endpoint or not. If so, you need to adapt this. I think that's a point which makes it not too easy to use this extension for everyone. It's not that you just import and enable the feature. You have to check all your layers if they really can do this. And perhaps you have to adapt that they don't use the address, they use then the connection ID in order to identify the other endpoint. For the Legion project, as far as I know, that's done. For other stuffs, I don't know. So that's just a slide to get people remember that there is also something more. Usually the time to switch active in the application layer may also be critical for the power consumption on the device, and this may affect the response time. So if the device waits for a response and the response takes 2 seconds, then this is a difference in order compared to, say, the response is in 200 milliseconds or something like that. So the point is really here, it depends a lot from the required functions. So if the application needs to store the data, load the data or something like that, we also need to be aware that in many IoT use cases, caching is not that effective, because if you have 100,000 devices and you assume that the 100,000 devices will report once an hour, then you will have the situation that the cache will always be the wrong one. That would change if the situation would be something like that the device wakes up and do then a lot of messages and then sleeps down, and then the same device comes up and so on. But if this is not the case, caching will not really work, and you need to consider this, that if your backend works with caching, you need to consider if this really works for IoT in your use case. It's also common to have vertical scaling. This means to put several processing stages on several machines. That's microservices and something like that. That's great to reduce or to improve the overall performance of parallel requests, but it also doesn't help to minimize the single response time. So be careful that a lot of stuff which is common in the cloud to improve the performance may affect the power consumptions of your device in a negative way. If this is the only solution, that's the only solution, but it affects the power consumption. So also sometimes one trick to reduce the power consumption is that you do not really send back an application response, that it is just something like, okay, we have received the data and we will process it. If this works for your application or not depends on the application. And just as I said, if you do not really consider those response times, and if you just use common cloud technology and that ends then up in large response times, then you may have larger energy consumption in the device. So maybe it's a good idea to always address this very early. So we have a next question.
Can I read the questions out so that people also know the question, Achim? Yeah. Yeah, don't worry. So what can be the potential issues if a cellular asset tracking solution uses a UDP protocol instead of TCP?
Yeah, the point is issue means something negative on my side.
I
and for me, it's only positive. So the benefit would be if you use it with this technology I currently demonstrate, this DTLS connection ID, the benefit will be that you don't need handshakes and that you will be very efficient. The second benefit, in my experience, is that you need less data because you do not need a handshakes. And on the top of that, that's also my experience. Sometimes if you have problems with the signal strength, so I would say it's in the gray, so that it is not longer that good working, then you will also get a benefit if you have only to exchange 2 messages to be successful instead of say 10. So from my viewpoint, you have a lot of benefits. There are downsides, but these downsides are more organizational ones. So if people are not coming to CoAP, they think that it is better to use, say, an MQTT or HTTP endpoint from Azure or AWS. Yes, if you need that, then you can't use for sure UDP. That's the point. But if you're willing to invest a little, and if you're willing to run your own communication endpoint, then I do not see too many issues with switching from TCP to UDP. Maybe there is this question is also based on the experience 5 years ago or something like that. So when I started with CoAP and DTLS, I think the implementation had a lot of bugs. I even recognized, say, after a year or something like that, that a lot of experts assumed that the IP addresses will always be static and will always be not changing. And with that, there was then a gap in between the reality the people are facing with the changing addresses and a specification that doesn't really address that. But in the end, I think the situation has now changed a lot. So now, not every implementation, but now there are implementations which are really well done, which has a high quality, which runs now for weeks without any issues and errors. And so it's more the question if you're willing to run your own VM on a cloud side or in your own IT. Hope that is the answer, right?
I believe so.
Good. So that was just a hint. Please do not forget the application layer, because it's really the point. If you usually use the common cloud stuff, that may result in long response times. And if you have long response times, this may also affect your power consumption in a negative way. I didn't make any measurements here because the point is that's so general, you can't really do this. When I did my measurements, I made also interesting stuff because or I recognized something interesting. It showed that after I have my response, until my device goes into the low energy state, it takes quite a long time sometimes. And this also consumes a lot of energy. Especially when we use this PSM mode, my results are that if you can use this with RAI is the release assistant indication, we'll see this, then the energy consumption is low. But if RAI is not available, and especially if we have a large ROC active timer, which we cannot really adjust, that's the first I know we can't adjust this one, then the consumption is really significant. So in the end, my point was, if I use PSM, that's great, but if it takes then that long that the device gets really into sleeping because I can't use RAI for whatever reason, then it is sometimes not really that good result. So let's go to the measurements here. So you see, if I use LTE-M with PSM, and as far as I know, release assistant indication is not really supported for LTE-M. then we see here that we have a phase where device just doesn't switch to sleep mode. It's 13 seconds and it takes up to 90 millicoulomb. This is really quite large. If you go back, or if you go back to the application protocol, this is really in the size of the application protocol. So a HTTP request takes 135 millicoulombs, and just to have the device going back to sleep takes additionally 90 for just lugging around. I'm not sure if this is really the intended stuff. If you just switch it off, it's also not just switching off, it is just deregistering from the network, something like that. Then it's much faster. Then we have 1.6 seconds and 25 millicoulomb. This is a better value. Okay, sure. I think that's the justification for the most stuff. If we can use the release assistant indication and PSM, yeah, then the values are brilliant. So I don't know if RAI is intended to be extended for LTE-M or not, or what's the real message behind. Maybe the point is also that I only test with a single request. Maybe they assume that it is always a sequence of requests, and then the relation will also change. But if you have only a single request, I think this lagging time after you're ready with the request is really something you need to consider. So with that, I think we have now seen all these different phases. I think this should now switch to the result tables. So as I said at the beginning, I measured any test case 4 times and took the average. So for HTTPS, we have a question. Chan said, you say you read it and I don't need to read it on my own?
Yes, but if you like, we can do the questions at the very end so that you won't be
okay,
disturbed.
Yeah.
They can wait a bit longer, and at the end I will read out the questions to you.
Okay, good. Yeah, sometimes I think if the questions are related to the shown slides, it's better to answer them in time, but we can also do it later on.
I mean, however you prefer. Let's do it now. Okay.
Okay,
okay.
Let me just read the question and then I decide if it is related.
Let's do it like that. Okay.
Okay, that's a question we can do later.
Yeah. Okay.
Okay. So that's our result. So we have HTTP. We have 95 millicoulomb in average with PSM, and the request itself, it takes 108 millicoulomb if we switch on off. But the overall consumption is different. You have seen the large lagging time. So this large time from when you're ready with the response until you power down that modem, or until the modem gets in the sleeping or off mode. And so the overall consumption is really interesting. So if we use PSM for this, then it's 205 millicoulomb. But if we switch it on and off, overall, then it's 157 millicoulomb. So we can save here something if we don't use PSM and switch on off. But please remember, switching on off may not be supported in that way by your mobile network operator, and it may end up that your device cannot re-register to the network at all. So it is just a hint. Maybe we should search for why are the numbers like that. So pretty much the same situation for DTLS 1.2 with PSK. That's when we need a handshake. So we have then an average consumption per request from 30 millicoulomb. You see it's a third of an HTTP request, so we can save 60% of the energy. Or it's 42 millicoulomb, that's also good. But also here we see if we do the overall power consumption, if we take that, then it's 128 to 71. So that's also not that good value. So it's always this lagging, which makes this really this lagging from the response to this power of us leaving, that makes this not that brilliant values. If we then go to the most advanced protocol, so to DTLS 1.2 connection ID, then the average power consumption goes down to 17. So we can also somehow save a lot of energy if we do not do the handshake there, or to 29. And also here the overall power consumption is then 106 to 55. So in my conclusion, you then say, okay, just assume on-off is a good idea. I'm not sure if on-off is really a good idea, but assume it's a good idea. So we have 55 millicoulomb is then the best one in class. So that's the 100%. And if we now compare this to a TLS handshake, to HTTPS, then this is with 157. This is close to 3 times more. So in the overall scenario, if we have only one request and not a couple of requests, using DTLS connection ID can save 2/3 of your energy. So okay. I think we can go to that then later on.
Yeah, let's do it. Let's do the questions at the end.
Okay. So here's the table result for narrowband IoT. I think here we see that, yeah, narrowband doesn't really support TCP. So here the numbers are really bad, but this is also, I think, close to everyone recommends not to use TCP over narrowband. But if you do it, then you have a power consumption of 306 and 260 millicoulomb. If you go to DTLS PSK, we have 82 to 124. And if you go to DTLS connection ID, then you have 61 to 72. We can also see that the overall consumption here, I have to say, I couldn't use RAI with TCP. I think this is lost here in the table. So the numbers of the TCP stuff are without RAI, therefore they have also a large lagging consumption in the end. And we have 370 millicoulombs, 300 millicoulombs, we have 100, 150, we have 79, and we have 98 millicoulombs. So I think the best in class here is DTLS connection ID with PSM. That's 80 millicoulomb. And we have then compared this to, say, the best one in for the HTTP stuff. Then this is the 300 millicoulomb, and then we have 380%. So it's also about 3 times better. So in my summary, yeah, if you use HTTPS with X509, then it takes twice the energy or more than twice the energy as if you use DTLS CoAP DTLS with connection ID. That's mainly because you don't need a handshake there. Switching on off in my measurement saves energy. As I said, if it is really a good idea to be used, something else. Narrowband, I think here we have the situation that with X509, it takes 3 times more energy than CoAP DTLS with connection ID without handshake, because we don't need it there. And if we can use it with RAI, then PSM is really saving also additional energy between 25 and 60% compared to just switch on off. Also, the comparison between DTLS connection ID with DTLS without connection ID. So this one needs, the one needs a handshake, the other one not. Then you also can save 25 to 50% of the energy. So not covered. I think in my experience, one of the large points which takes power consumptions are really the network searches. And this is not that easy to determine how much this takes. So in the last weeks, I was in Greek, and there we only have NB-IoT. I run 2 devices. One I left in the hotel. This was a stationary one. And after 11 days, there was 60% battery left. The other one I was taking with me, moving around, and this goes down then to 26%. Both has exchanged about 1,700 messages. The moving one needs also 150 mobile network searches additionally. So the point here was the searches really take energy, and I think they will influence how long a device will run in the end. So some references if you want to retest or verify the results. There's a small open source project. You have here a link. It's a feature branch there, power consumption comparison. I have also prepared some slides. The server is the Eclipse Californium Sandbox server. I use the plug test server there. So you can also use this if you want to retest it. I have also a slide with some more links. So there is a comparison from the telecom. There is also analysis from Nordic Semiconductor, and there's also analysis and a study from Harald Naumann. So now we can go to the questions. So what tool do you use to measure energy consumption? But I think, Chance, you want to read?
No, that's not a problem. But okay, let me read them. So what tool do you use to measure energy consumptions in your measurement?
This is this small tool for Nordic Semiconductors. This is the Power Profiler Kit 2. I think it's about 100 to 150 euros to buy. It's a very small and nice device. I hope it's good enough and doesn't make too much wrong measurements. Okay, next one.
Thank you. Next question is this is an additional note from Bruno. So the RIA is also available for LTE-M, but requires that the operator enables and supports it. In my network, it supports.
That's a very good news, because really RIA would be very, very, very helpful. That's really good. So maybe we then have just to continue to ask the operators to also enable it. That's a good news.
Exactly. Another clarification question. So you mean by PSM, the on and off through the PSM mode?
No, I think, so there was, in the weeks before this, before I prepared my analysis, there was some sayings that some say, okay, you can use PSM, but maybe the operators are not really supporting it. And so someone said, okay, in his experience, it's even better to just really switch on and off the modem, really power on, power off the modem. CFAN 0, CFAN 1. And yeah, I recognize that I never did this. So I never did before this. I never did really switch the modem off and on. And so I thought, okay, that's a good idea. I just try it out. And I was really surprised that if you don't have RIA, switching on, switching off is not that bad. But it's really CFAN 0, CFAN 1, where PSM does this sleeping mode automatically. So PSM is something like the start-stop automation for the car, and switching on, switching off is turning a key on and off. Okay.
Okay, thank you. So the next one is also some sort of feedback, but let's take the questions out of this, and maybe
I think we can go to this. That's not a point. I think I tried. I think I really tried to make this not as a theoretical stuff. It is really in practice. And if you can tell me a TLS connection which can use PSK really, so that everyone can also use this, then we can also compare it with PSK. But that's the point. So if TLS mainly uses X509, and that's what is mainly available, then I think we should use this as common case. And in the end, I think you need to see that I do not really compare the handshakes a lot. What I did was, over years, build up a specification, this DTLS connection ID stuff, where we just don't need a handshake. There's also an alternative technology. This is this OS Core stuff from, I think it's Ericsson. This is also something where you don't need a handshake. So the people are really going forward and to make the handshake completely obsolete. So for me, it doesn't really make that sense to have other stuff there. And okay, so let's go beta. I don't know why you should consider good connection or bad connection. I think I started with that because I'm not an engineer, electronic engineer, a modem expert. I'm a protocol expert. I don't know if, if there is that much difference, if this gets better or not. I think DTLS will work better if it's bad, but that's not something I really can consider. Oh, scaling of CoAP message when conformal messages are required. And sometimes I really don't know what the people are thinking. If you run California on a big box, you have no problems to run 50,000 messages confirmed per second with encryption. I don't know really what this is good for. What is large payload? When large payload is required, I don't think that you really concern the power consumption. CoAP offers blockwise, but it's really that the point is if you have a large payload, I don't think that all this stuff is working. So you can then have something like, okay, if I have large payload and I only want to send this once a day, I think that's what some people do. Yeah, at that point, even HTTPS may get better, that's clear. But if you do such a comparison, I think you need to focus on what you really want to demonstrate. I think you have other questions, and those questions are not answered in my comparison, but the good point is you have the tool set up so you can make these comparisons with your questions as you want.
Yeah.
So yeah, biased and not helpful. Yeah, I think that's really true because basically I'm the developer and the expert who has defined the specification of DTLS connection ID. So yes, I do this, and yes, I do not really analyze in deep what TCP and TLS can do, but if you can also not easily demonstrate what TCP and TLS can do. That's really a point. So after several months, nobody really showed up and demonstrated how we can do this better with TLS and TCP. I hope that's explains it.
Yeah, maybe I was also not clear in the beginning about the content of this this presentation, and maybe this participant was looking for some other content. So sorry if there is a lack of communication from my side, but the presentation content was apparently different than the expected one. Okay, moving on with another question. So Bruno asked, why on LTE-M DTLS 1.2 CID PSK on and off have better results than with PSM, and on the other hand, NB-IoT is not the case? Very good question on slide 15 and 16. Can you maybe go back on your slides?
The point is with LTE-M, I don't have RAI. So if I don't have RAI, then the lagging time, this means after I'm ready with the response until the modem gets to the power down state, takes very long. So with LTE-M, it is was better to use on off, and with narrowband, it was better to use RAI. And in generally, this is also very surprising because it is said usually vice versa. It's surprising that LTE-M is under good signal conditions. So that's the preconditions. I have very good signal conditions here. Under good signal conditions, LTE-M is better than narrowband IoT. This is surprising. And it's not only my result, it's also the result of the last research from Nordic Semiconductor. So you can go to the Nordic Semiconductor page and look on their last results. And they made a new research, and they found in their environment also that LTE-M performs very well, except if the signal condition goes really very down, very bad. So yeah, LTE-M is better, and on off on LTE-M is better if we don't have RAI. If we can enable RAI, I think RAI will be better, or PSM will be better, and a narrowband, it's something else.
Bruno also mentioned that he has RAI with LTE-M in his operator, so maybe his experience is different. Maybe
maybe that's then the stuff. Yeah, sure. So I don't have RAI for LTE-M, and therefore I have a large power consumption after the message exchange.
Okay. Okay, moving on with another question. What was the difference between static and moving narrowband IoT devices?
Okay, so I think the static one, that this doesn't require too much network searches. But when I was moving and I was sometimes climbing in the mountain or trekking in the mountain or trekking in the valley. So when I was moving, then the device needs frequently to search for a network. And I guess even sometimes the device didn't find the network. So the difference was that one device spends to close no energy into search networks, and the other one was permanently searching networks 150 times into 2 weeks, and that makes the difference.
Okay, thank you. Next question. What is practically used maximum number of repetitions in coverage level 2 in narrowband IoT?
No clue. I think that's a question for modem experts.
Yeah, I have no clue. Thank you. Maybe.
Okay, yes. What about security with PSK? I think, okay, for security, I think we have 2 aspects. So let's start with the one. I think something is secure as long as you keep the private key or the secret key secure. And there are several mechanisms for doing that. Either you have a HSM or you just enable some flash fuses, which then disallows you to read the stuff out. But the main attack vector, in my opinion, is here that you can read out either the secret or the private key. And in that attack vector, that's pretty similar, the security there. Okay, on another aspect, this means that if I use a private public key, then the point is the private key is only in one peer. So only one peer has this, the other one doesn't have it. So if I put on a few, like there is a device owner and there is a cloud owner and there are different organizations, then the point is PSK doesn't really match well because they share then a secret and later on they blame each other for giving out that secret or do not protect that secret. So that's more a point if you have an organization where your device and your server belongs to different organizations. I considered also to provide values for raw public key. So this means this is also a private public key stuff, but not X509. I think it was more the time for preparing this comparison, which makes me not doing so. And again, the point is you can use X509 also with DTLS. That's not a point. But for me, X509 makes not that sense in IoT, but there are others who think it makes sense. Anyway, if you use X509, PSK, or raw public key, everything is great. If you use DTLS connection ID, you will see that the influence, what you take there, gets down. So it gets lower and lower, and therefore I didn't really consider too much about how we do authenticate the other peer.
Yeah, just to follow up, he said that he's talking here about the side channel attacks via software-defined radio to crack AES. Just to explain, but
yeah.
Okay, okay.
I don't know what the people, I think sometimes it's very easy. So the experts are deep in, so they get you a little part of the information and the other expert can't understand it because he's not in this domain. So yeah, I'm not aware that there is something where you can hack into PSK easier than into raw public key or X509. I think the most point is how can you read out the secret or the private key, and that doesn't depend on PSK or X509.
Exactly.
But yeah.
Yeah, okay, but I would like to go back to the static and moving narrowband IoT device question, because there is a follow-up to that one. So can you go back to your slides where you explain the differences, because he just needed the percentage of them. So maybe we can get some numbers.
For the moving and not moving? Yes,
exactly. You had this, yeah, this one. I believe this one is needed here. So maybe we can keep it on the screen and maybe.
Yeah, just maybe to say this is a Thinky 9.1. So it's this Nordic modem, not a development kit. It's the orange box.
Good old orange,
orange box. I took 2 of them into occasion to do some tests. And the one was staying in the hotel. This is the 60% one with close to no network searches, and the other one was searching very heavy during the network, and then you have really that different results.
Okay, thank you. So another topic I'm moving on. So is your session key related to the session identifiers as described in RFC 5246 or session tickets as depicted in RFC 5077?
I don't know what the session key and session identifier should really be, because the connection ID, if this is the thing, this is RFC 9146. And it is not really related to the identifier or to something else. This is a new artifact, so it's not a session ID. A session ID can use session resumption with different IP addresses. Using session resumption and the session identifier, this was really the focus, I think, 4 years ago. I also focused a lot on this idea of using session resumption and the session identifier. But the point with narrowband is that doing this abbreviate handshake with the session resumption is also pain with narrowband. And at that point, with my first experience in narrowband IoT, I switched and joined the DTLS connection ID stuff and implemented that and tried it out. And for me, this is much better. Hope this helps.
Thank you. And the last one is, I guess, a confirmation. This presentation fully confirms our field findings. The industry had a big mess with power save mode in LTE-M, as they don't say power, but increase power, very true. And the RAI in LTE-M is prior testing, very rarely supported. I believe it is the same for your network. And I take this as criticism from my side, from the operator perspective. It's very true, unfortunately.
I think we should not really overestimate or overemphasize the stuff. I think as others have already also said, if you transmit more data, not just one single small message, if you transmit more data, then this gets less relevant. But I think that's really it's really how the technology will go which way. If we want, because it's really a great technology, so NB-IoT and LTE-M, it really develops very well after the last years, in my experience. And with this technology, it would be possible to really also send spontaneously some messages, smaller ones, and really have much more data in real time. And if we benefit from this real-time aspect, then it gets important, perhaps, that we improve this switching on, switching off. In this case, is this switching off. And yes, it would be great if the operators go to support this more and more. But on the other side, it may be also that we can even now use this and build applications. Maybe we then need to recharge the device after 4 weeks and not after 6 weeks, but it's still usable. It's still usable and it's improvable, and that's really cool. But it's really nice that others have the same experience. So if we talk about real experience, then I think a lot of people share the same.
Yeah, exactly. And yeah, thank you, ASUS, for your feedback. Very interesting conclusions. And with that, I believe we are through with the questions. And thank you very much, Achim, for sharing your experience and for answering all these questions and joining our session, of course.
You're welcome. You're welcome. And I also really welcome critical questions, but I would really, really welcome if we then have also really real world demonstration and examples. So yes, a lot of people say, yeah, you can do TLS with resumption tickets and abbreviated handshakes. Yes, you can do in theory, but please do it in practice. Come here and practice it. Come here and show that you really can do it, and it's not only on paper. So that's, let me say, that is really what costs me now a long time to make CoAP and DTLS, not on the paperwork. Hi, Jansen.
Hi. I'm very sorry.
I'm not sure if the last half was online or not. It's okay.
No, I guess people are still there, but I am very sorry. I lost connection. I don't know what happened. But I guess we were, sorry, Achim, that interrupted your speech. But yeah, I guess we can then conclude the session before I lost my connection again. And thank you so much once again.
Again?
I just said thank you so much once again for joining.
Okay, yes. And I also thank you very much for having the opportunity to present my information. It's usual that if you So really a long experience also in my company. It always has some people who believe in their solutions, and if there's a different solution, it gets always a hard discussion. And
Always.
yeah, so I also know that a lot of people say, yeah, but why did you waste your time with UDP and instead improve TLS? That's okay, but from my viewpoint, there are so many brilliant engineers using TLS and TCP, so I think it's up to them to demonstrate how it works best, and not to me. So, yeah.
I see your point.
Yeah.
Okay, then. Thank you very much, Achim, for that presentation. And thanks everyone for joining. In the afternoon, we have our final session with non-IP data delivery. This will be a similar context about also power saving around the non-IP data delivery. So
Okay.
I hope to see everyone there, and have a good day.
Thank you, Janset. Bye.
Bye.